And those equations were the equations that Schrodinger used to solve the hydrogen atom. We used them for the particle in a box, but he used it for the hydrogen atom, an electron orbiting a nucleus. So he had a potential energy term and everything. But some of those equations were just applied to the problem. There really wasn't a derivation of the reasons for using those equations. Okay, we thought, well, let's just assume that matter is acting like a wave, and let's apply these wave functions to it. But notice that's an assumption. And so that's what we're talking about here, the quantum mechanical postulates. So there are certain assumptions that Schrodinger used that turned out to match the data very well, but they're still assumptions. So let's look at the assumptions of this whole system. And so these are called postulates. And if you use it as a verb, you're postulating something, you're assuming something is true in order to reason a certain way. If it's a noun, then these are the postulates, or these are the things that are assumed to be true for reasoning. And in math, it's just your assumptions, your basic assumptions. You're going to start there, and then you're going to move forward. So this is just the postulates that are the basis for quantum mechanics. These are things that are assumed to be true, but we really can't prove them. Now, we have confidence in quantum mechanics because if we use this math, we can reproduce spectroscopy. Okay, but that doesn't really prove the wave function's existence or that we have the right starting point. There may be another starting point that also produces the spectra. There may be another starting point that has more reasonable inferences, philosophically, and so on. But these are the ones that Schrodinger used and that have been passed down and that seem to match the data very well. But like I talked last time, what is the wave function? We really don't have that answer. We're just assuming that it matches nature. And then we're doing the math and seeing that it matches the spectra really well. So postulate 1 is that the quantum mechanical system is completely specified by the wave function. And so I have a wave function here. Can I get you to help me out? So let me stand here. Just hold this very still, okay? Right there, okay. So this is what we mean by a standing wave. You stay still and I'll be the driver. There we go. So that's the ground state of a particle in a box. You see just one load. And you see how slow it is, very low kinetic energy. But if I change the kinetic energy, now I'm in quantum state 2. And I have a node in the middle. Okay, and you see it's going faster. And it has more curvature. It goes up and down more. So that's more kinetic energy. Because the Schrodinger equation is the second derivative of the wave function. The first derivative is the slope. The second derivative is the change in the slope or the curvature. Let's try to get the 3. There we go. Yeah, that's good. See, much higher energy. It goes as n squared. So I kind of have to put, this is, the first one was 1, the second one was 4, this one is 9. If you think of the squares of n. Yeah. So they're not equally spaced. I can try 4, but then I've got to go to 16. I've got something there. I don't know which one it is.
Yeah, 5.
Okay, so I went to 25. Okay. So that's n equals 5 state. Thank you. So we're saying that describing these systems with the wave can fully characterize that system. Now, there's some requirements of this. One is that if you square the wave function, you have the probability distribution. And so this square modulus, now the modulus part is this complex conjugate piece. So we say the square modulus is not just the square of the wave function, it's the square modulus, which means you have the complex conjugate times the wave function. So I think I showed this last time, like if psi is equal to A plus IB, then psi star is A minus IB. Okay.
Imaginary stuff cancels out.
Yeah, the imaginary parts cancel, yeah. And so it it also ensures that we get a real result when we integrate over all space. So this probability that the particle will be found at time t in a spatial interval of surrounded by, this x plus or minus delta x is given by the square of this wave function. So that means if we integrate these across the whole box, tiny little pieces, and we add all those up, essentially we take the integral over all space, then the probability will be 1. And so this is the full wave function with time and all 3 coordinates. That would be an enormous integral. So you have 4 different integrals integrating with respect to x, y, z, and time. And that over all space would equal 1. That would be what we call normalization. So we're going to normalize those wave functions so that this condition is met. This is we call this, there's a name associated with this that I'll use occasionally. This is the Born. See, I don't know if it's an approximation or a criterion. Let me see. Where does it say?
If it's for learning.
It's this right here. This is right here. This probability piece. Probability. Okay. This piece is. This whole thing is this one is the Born interpretation. So this particular postulate, part of this postulate is given to Max Born. And so a lot of times people will say the Born condition, which is essentially that the wave function squared is the probability distribution. That's really all it is. Okay. But what that means is that our wave functions have to be normalized. Now for this particular section of the course, we're not going to do the multiple coordinates. We're just going to do it in one dimension. So our integral simplifies to just the wave function as a function of x. Much simpler. This means our wave functions have certain criteria that they must meet. And so this wave generating device wouldn't be very good if it was broken in the middle. So our wave functions have to be continuous. If it was bent, either it wouldn't make a very smooth wave function. Notice also, though, that this first derivative, because the Schrodinger equation takes the second derivative, we need to have a continuous first derivative. Because right here, the first derivative is double valued. It's not defined. If I'm coming from this side, it's negative, and if I'm coming from this side over here, it's positive. And so it's going to be, if I plotted the first derivative from the left, it would be below 0, and from the right, it would be above 0. And so it would be broken in the middle. It wouldn't be continuous. So we couldn't take the second derivative. It also needs to be single valued, so it shouldn't double back on itself like this. And then if I'm going to integrate over all space and that needs to equal 1, I can't have it go to infinity in the middle because I can't divide infinity by any number and get 1. Okay. And so then we also need our wave functions to be independent of each other. I want wave function 3 to not be dependent upon wave function 1 or 5 or 2. And so we call that orthogonal. And so if you notice here, if we have, say, n prime down the column, 1, 2, 3, 4, 5, and n across the top, and this is the wave function times the other wave functions. So here I have, this one right here is wave function 5 times wave function 1, integrated over all space, and it's equal to 0. And this is wave function 4 times 1, and this is 3 times 1, 2 times 1. Only when it's 1 times 1 do I get 1. And all the off-diagonal elements are 0. So that's sort of a representation, this table, of what we call the Kronecker delta. So we say that orthonormality is given by this condition. This delta n prime n, this delta is equal to 1 when n prime equals n, is equal to 0 when n prime is not equal to n. And so this is orthonormality right here. It's both orthogonal when n does not equal n prime, and it's normal when n equals n prime. Okay. This is still sort of required by that Born interpretation and the postulate 1. So this all falls under postulate 1. The wave function is used to characterize all particles in nature. Now, we can show the math here. I'll just go through it quickly, just so that you can see it's not that difficult. So this is Dirac notation. We're going to have n prime equals n. And so we'll go ahead and put our wave functions together. Now, our wave functions, let me back up a little bit to this right here. These criterion are met by some very simple wave functions like cosine and sine. And if you combine cosine and sine and you have an imaginary number in there, you have the exponential function for Euler's formula. So e to the minus ix or e to the ix, and that is cosine plus I sine. And so sines and cosines and exponentials are related. You could also use a Gaussian function, so e to the x squared. So those are the only functions you really need in spectroscopy, PChem, quantum mechanics, are these Gaussians or these exponentials or cosine and sine functions. So if you know how to take the derivative and the integral of those four functions, you're good. I mean, there's a whole lot of other functions out there that you could study in calculus, and in PChem we really just use those four. In fact, the software Gaussian gets its name from using Gaussians as the wave function. It's not the line shape function in that case or the statistical normal distribution. Gaussian's called Gaussian because it uses Gaussian functions as the wave functions. Okay. But we're going to use sine. So we start with sine. Let's put a constant out front. This is the normalization constant. And so when we say normalization, we're determining what is n. Okay, so we set up this integral of the wave function times itself, and we set that equal to 1. And so that's our normalization criteria. So we're going to solve this integral and then solve for n. So the arguments inside the signs are the same, and so we can combine them to make sine squared. And then we can use this trigonometric identity to get rid of the sine squared. And so then we end up with an integral of a sum, because this is, again, this 1/2 minus 1/2 cosine. So that's pretty straightforward. It's 2u, and so the 2 in the denominator canceled, and then we have a 2 in front of the n. Okay, so now we can set up these two integrals. The first integral is the easiest integral you'll ever do. Integral of dx. Okay, so you get x out of that one. And then the integral of cosine is sine. And so we have this integral. We've finished with the integration, and we have our limits of integration here. And so we have this whole argument evaluated at L over 2, n for x, and subtract this whole argument at minus L over 2. So expanding this out, we have these minus signs here that are going to cancel. We'll cancel those next. We have 2 times 2, which gives us 4 in the denominator. And then we have these things. So let's cancel some of this stuff out. The L's cancel, the 2's cancel. Okay, and so we have a 2 n pi here. This cancels, this cancels. And we have an n pi minus an n pi. So this is 0. Okay. So what's nice is we end up with this sign of 2n pi. Now, if you remember sine at 0, it goes up and down and up and down. Oops, that's bad. It crosses 0 at every integer multiple of pi. And our quantum numbers here are integers. And so since our quantum numbers are integers, it's always the sign of something pi. And so it's always 0. So the sign pieces are gone. And all we're left with is this right here. So we have 1/4 plus 1/4 times these other functions. And so that ends up being n squared L over 2. We can rearrange this algebraically and solve for n. And now I know what my normalization constant is. This will make my wave function times itself equal 1 when I integrate over all space. So we have a normalized wave function. Let's make sure we have an orthogonal wave function. So with these arguments inside sine, if we multiply these with different quantum numbers, do we get 0? And so let's look at that situation. So now we're going to leave n prime in there. We're not going to make n prime equal to n. So we're going to leave these alone, this n prime and n prime. So we can't combine our signs into signs squared in this case. We do have our normalization constants in there, and they are multiplied by each other. The square root goes away, so this is out front. And so we have this sine u times sine v. And we can look that up, sine times sine, and we can find the cosine difference in sum. Yeah, so we have cosine u minus v, and we have cosine u plus v. Yeah. And so this is easy. We now have a single cosine too, and we can integrate those. Okay. We can simplify things too. So I've got the x's here. So I'm going to combine these x terms on both sides, and I end up with this. So I end up with this difference over L times x, and this difference over 2, this sum over L, and this sum over 2. And I'm going to split the integrals. And so I take the integral of cosine, I get sine. I have the same things here. And then I'm going to evaluate these at L over 2 plus and minus. Now notice the L's are going to cancel, but I'm going to end up with a 2 down here. So I'm going to cancel. This L will cancel, and I'll end up with a 2 here when I put that in for x. And then I'm going to subtract this whole function again with the minus L over there. And so we see this simplification here. This first one just ends up with this difference. And if you need to go over these steps again, just go look at the video and you can go slower. So we end up with this difference. And again, the quantum numbers are integers. And so the difference of integers is also integers. So we have sine of integer multiples of pi here. This is the sine of 0, also going to be 0. And once again, the quantum numbers are integers, and so sums of integers are also integers. And so that's going to be the sine of integer multiples of pi, which gives 0, and this is going to be the sine of 0, which gives 0. So all my sine parts are 0, so it doesn't matter what these fractions are out front. And so we end up with 0. So that's orthogonal. So that means no matter what my quantum numbers are, if they're different, we have a 0 integral, and if they're the same, we have 1. So we've proven that we have orthogonal and normal wave functions for a particle in a box. We have these observables. So every measurable property, there exists a corresponding operator in quantum mechanics. So this is postulate 2. We operate on a wave function, and that wave function, postulate 1, that wave function represents matter in nature. And postulate 2 is if we operate on that wave function, we get some result back, a real mathematical real result that is that observable quantity. So we can operate it and get the energy, we can operate on it and get the momentum, we can operate on it and get the position. So there's an operator for every kind of measurable quantity in quantum mechanics. And so this is how we simulate experiments mathematically. So we'll take the wave function, and if we know the wave functions for vibration or electronic orbitals, we can operate on those wave functions and we can get the observables for our experiment. So this is the practical use of quantum mechanics. And that's what I did with that simulated spectrum last time. Okay. So these are the operators. We have momentum operator, kinetic energy operator, position operator is just that x-axis. The potential energy depends upon the system. For our particle in a box, we put it on a wire, we said it's 0. So V equals 0, it doesn't do anything. But for a harmonic oscillator, vibrational motion, like a CH stretch, then that's going to be the minus kx squared, this Hooke's law. Yeah, for a harmonic oscillator. If it's for an electron around the proton, for a hydrogen atom, that's Coulombic potential. So what's the distance, the average distance of that electron from the positive nucleus? That would be the V term. So V depends upon the system. The total energy, this Hamiltonian here, let's see. Is the kinetic plus the potential. So the kinetic energy piece is here, and the potential energy piece is there. So it's the total energy operator. Notice the second derivative here. This is the curvature of the wave function. The first derivative is the slope, and the second derivative is the curvature. And so like I showed with the slinky, if it's more curved, it has a higher energy. When we got to n equals 5, you saw how curved it was. If it crosses 0 a bunch of times, it's got a high curvature, which means it has lots of nodes. So you can look at wave functions and see how many times they change sign. If we were to take a snapshot of that wave function, we would say the sign for the top pieces is plus, and the sign for the bottom piece is minus, and it's changing sign a lot, plus, minus, plus, minus. So that means it has a high curvature, has a high energy. Yes. So you can look at a set of wave functions. If you got 5 wave functions, and you could say, okay, this one has more sign changes, more nodes, therefore it has a higher energy. We could also look at the p orbital versus the d orbital. Right? We have plus, minus, and plus, minus, plus, minus. So the d orbital is higher in energy than the p orbital because it has more curvature, more sign changes. Okay. Now, postulate 3 deals with eigenvalues. So these equations are eigenvalue equations, and we'll explore the Schrodinger equation next, and I'll show you what that means. So the properties of the wave function and the operator will cause this system to be quantized. Now, what I mean by that is in our system, we put an electron on a wire. We've confined it to a space. We call it a box. Most of the time, boxes are 3-dimensional, but we just have 1 dimension. It's a 1-dimensional box. It's a line. We put the electron on that line, and we said, you can't go past the length of the box. Okay? That's the boundary condition, and that sets up our quantized natures. Now, that boundary condition is really governed by the potential energy, because at the ends of the box, the potential energy goes to infinity. So it's the properties of the wave function and the operator that give us quantization. And a lot of times it's the properties of the potential energy curve that give us that quantization. That's what's causing our system to be confined, to make a standing wave. Okay? And then these eigenvalues are the quantized observables. So the energy, the momentum, the position. So let's look at an example. So this is an eigenvalue equation, a Schrodinger equation, and it's eigen means same in German. And it's really focused on these wave functions. See, this wave function is the same as this wave function. That's what makes it an eigenvalue equation. You operate on a function, and then that function comes back. And some constants come out front. So let's go ahead and walk through it. We have our 2 normalized wave functions, or our normalized wave function on both sides. We have the Hamiltonian operator. Inside our box, the potential energy is 0, so we don't have any V term, just have the kinetic energy term. And over on this side, we have the energy. The only thing we have to do in this equation is this piece right here. We're not finished. And so let's have a discussion real quick about how do we know when we're finished. We've written the Schrodinger equation, but how do we know when we're finished? Well, we still have derivatives, we still have integrals, we still have things of that sort. So you're not done until you've finished all the integrals and all the derivatives. Okay. And then a second criterion I like is at the end, let's simplify it so that the quantum numbers are separate from everything else. So that's another piece, because then you have a measurable result. And so I'll talk about that in a second. So we're not done. We have to take the derivative. So we take the first derivative. So the derivative of sine is cosine. And so then the pieces inside the sine come out. We have these coefficients of x that come out here. Okay. And then we have another derivative to take. So the derivative of cosine is minus sine. And so this piece right here has gone away because of the minus sign. And then another piece of n pi and L come out. Okay. And we got our wave function back. So we have psi now. And we have psi we're done with all the derivatives. So we have these constants here. And so these constants are the eigenvalues. They're the quantized energies. So that's it. We solved Schrodinger equation in 3 lines. It's like supposed to be complex. Now do it for the hydrogen atom. It's pretty complex. Okay. But all we did was take the second derivative and we're done. We've got the energies. Now it could be simplified. And so let's simplify it a little bit. Now this h bar here is h over 2 pi. And so we're going to have that cancel this pi over here. We've got h bar squared, and so there's a pi squared here. So the pi squareds are going to go away. We're going to have h squared on top, and then this 2 turns into a 4, which is then multiplied by that 2. So this is where the 8 came from. So you go from 2 to 8, and you're wondering what happened. Well, the h lost its bar. Okay, and the pi's are gone too, because it was h bar was h over 2 pi. I've got these constants out front here, and I've got the quantum numbers. But these right here, that's the good stuff. Why? Because that's where my physical properties of my system are. That's where mass is. That's where the size of my atom, ion, or molecule is. Yeah, these are the physical constants. That's where Planck's constant is. I mean, we're kind of done with Planck's constant, but at the beginning we weren't. Right? So this would be a way to discover Planck's constant as a fundamental property of nature. So these are the good things that we're after as scientists. And the quantum number is useful. So in a spectrum, we might have, several peaks, and we label them with quantum numbers, like 1 to 2, and 2 to 3, and 3 to 4. So we label these with the quantum numbers here, right? And then we can solve for bond lengths, okay, dipole moments, mass of the system, rotational constants, how much inertia the molecule has. So we can solve for things about nature that we can't see. So these are tiny lengths, tiny masses. There's no way to weigh it on a balance. There's no way to measure it with a ruler. We use spectroscopy to get down into the invisible parts of nature. And so that's why we pull those out and leave the quantum numbers over here, and then we pull out the constants so that we can get to the invisible parts of nature. And then we have these expectation values, which is just a different form of the Schrodinger equation. Notice we left multiply and integrate over all space, and we're able to get these average values, but it's essentially the same math. Now for spectroscopy, notice I was doing this peak was 1 to 2 and 2 to 3 and 3 to 4. That's that transition equation. So in spectroscopy, every peak is a difference between energy levels. We have to solve Schrodinger equation to get the energy levels, but then we have to take differences to get to the spectroscopic horizontal axis. So that's called the transition equation. So we have transition energy, transition frequency, and transition wavelength equations. So I've done this for the general case. So we have n going to n plus some delta n, right? It could be a change in 1 quantum state or 2 quantum states or 3 or whatever. So that's what delta n is, how many jumps I'm taking, okay? And I'm doing this in the general case. Those of you who had PChem1 with me, we didn't do the general case. We did specific cases. We did for a change of n equals 1, delta n1, or delta n2, or delta n3. This is a general case, just in case you remember. Okay, so we pull those constants out front. We solve this little bit of algebra with this quadratic equation. And so we just multiply this n squared through, and we end up with a minus n squared, canceling the n squared. We have this delta n, which I'm going to pull delta n out and put it with the constants. Or at least I pull one of them out. And so I have this delta n pulled out. I still have one inside. That's okay. But I wanted this piece here. This is the quantum number piece. That's the quantum number piece. And this is the physical constants piece. Now I can take this energy is equal to h nu. Okay, I'll go ahead and put delta E because that's what we're talking about. So I can solve for the frequency by just dividing delta E by h. And so that square is going to go away. So this looks a lot similar, but it's kind of gotten blasted by. Erase that. Okay. So that's the transition frequency. So if we were plotting a spectrum where the horizontal axis was frequency, then this is the equation that would tell us the locations of those peaks. And then if we were plotting by wavelength, what's new? C over lambda. And then lambda is C over nu. So now we have the speed of light in here. There's my C. Everything else is inverted. And so this is a very good result. I mean, let's look at this equation. In the wavelength spectrum, so if I've got a spectrum here by wavelength, and I've got a peak here, that's for a particular mass and a particular length. If I increase the length of the system, I get a redshift. So as L goes up, wavelength goes up. As mass goes up, wavelength goes up. You see that down here? Yeah. As quantum number goes up, wavelength goes down. As n goes up, wavelength goes down. And so this might be the n equals 1 peak, 1 to 2, and then down here is 1, 2 to 3, 2 to 3, so on. Now that's for delta n equals 1. If I have a delta n equals 2 or a delta n equals 3, then those are also going to be delta n equals 2 or 3, that's in the denominator, so it's going to make lambda go down. Delta n over here is in the denominator, so lambda is going to go down. So if I'm jumping further, I'm jumping a higher energy difference, I have a shorter wavelength. Okay. And then the postulate 5 is just time dependence. So there's also a time dependence to the wave function, which has this operator out front, IH over 2 pi. We're not really doing anything with time dependence in this course, but it's a part of the Schrodinger equation. And that's it. So we'll see you next time. I'm going to try to do some examples next time in Gaussian, so we'll see how this can apply.